Good morning all, welcome you session 2 on system software. Today I am going to explain the machine architecture, that is the SIC XC machine architecture in this session. So here whatever the machine architecture just we are taking, for every machine architecture the aspects are same. So these are the main aspects just we are going to consider for any kind of machine architecture. That is the memory, registers, data formats, instruction formats, addressing modes, instruction set and input output instructions. So in the last session when I have explained on whatever I have done in SIC, the same thing is there in SIC also. So here is the extensible version of SIC, that is a standardized. Some of the informations or instructions are little bit more than that of SIC machine architecture. So here just we'll take the same thing and just I'm going to elaborate all those things one by one. So first we'll take the memory. So memory, as we know that just we are talking about the primary memory structure. So here whatever the primary memory structure just we are taking, so as of course a single word length, it is of 3 bytes. It is supporting, that is byte addresses. Again it is providing, that is SIC machine architecture, it was providing only 2 to the power of 15 bytes of the memory for user space, but in this case it is providing 2 to the power of 20 bytes, almost 1 megabyte of memory for the user spaces. And when we are talking about the registers, along with the registers, accumulator, linkage registers, index registers, program counter and the status word, along with those some of the additional registers are there. So each register length it is of 24 bits in SIC and in SIC XC also. So in the SIC it was supporting only few special purpose registers, that is the accumulator, index registers, program counter, linkage registers and the status word. Along with that, in the SIC XC it is also providing 2 more special purpose registers and 2 more general purpose registers. So those are base register, then 2 general purpose registers, SNT, and another register it is floating point. Registers. So here these 3 registers are 24-bit length and the floating point registers it is 48-bit length. Base register is for addressing purpose, floating point register which is used to store the floating point values, and these 2 registers, that is the SNT registers, which we are using for storing some kind of intermediate data while computing something at the execution time. So at the same time each register it is having its own number. So in the SIC machine architecture, while constructing an object code for each and every instructions, whenever the registers are involved in that particular instructions, instead of using that name we are using its number. So for that just each registers it is having its own number. The base registers, the numeric value it is 3, general purpose registers SNT it is for 4 and 5, for floating point registers then number it is 6. So these are additionally, along with these it is providing 4 more registers for different purposes. Base register, 2 general purpose registers for storing the intermediate data and the floating point registers which is having a length of 48 bits. So then when it comes to that data formats, so please do remember all the registers except floating point register it is 24-bit length. Then we'll move to that data formats. So data formats, as of course it is supporting different kinds of data formats, that is the integer, characters, then negative numbers and all. In SIC it was not supporting floating point numbers, but in SIC XC it is supporting floating point number also for storing, for computing some kind of arithmetic operations and all. So here the floating point to store the floating point values, it requires 48 bit of length, 48 bit of length. So among those 48 bits, it is bifurcating, right? So the one bit, the first one bit, it is used to represent the sign of a number, whether it is a positive or negative. So the next 11 bits, which is used to represent its exponential value or exponent value. The remaining 36 bits, which is used to represent the fraction value of that particular number. The first bit, which is used to represent the sign bit, and the next 11 bits, which is used to represent the exponential value, and the remaining 36 bits, which are used to represent the fraction of that number. So this is, along with that, the integers, again character, and the negative numbers. It is also supporting the data format for floating point also. For integer, we are using one word length. It is nothing but it is 3 bytes. It is 3 bytes. For single character, 1 byte is required in the form of ASCII value, and for representing the negative number, we are using the 2's complement method. So the most important thing in SIC-XC, it is instruction formats. The most important in SIC-XC, it is instruction formats. In this case, in the SIC machine architecture, it was supporting only one instruction format, that is the standard instruction. For every instruction, it is of 3 bytes length. So means among that instruction, it is 3 bytes means 24 bits. The first 8 bit it is for opcode. The next bit, it is to represent the addressing mode, either direct or index addressing mode. The remaining 15 bits are used to represent what? The address. But in this case, for some of the instructions, we cannot fit the value in 15 bit of information. In that 15 bit of informations, we cannot fit that value. So for that, we are using different kinds of formats for different kinds of instructions. So there are 4 different instruction formats are there. So we'll discuss one by one now. So the first one is format 1. Format 1. Format 2, format 3, and format 4. So format 1, it is of 1 byte length. Format 2, it is 2 bytes of length. Format 3, it is of 3 bytes of length. Format 4, it is of 4 bytes of length. So we are using different kinds of instruction format for representing different kinds of instructions here. So first I'll go with the format 1. For what kind of instructions the format 1 it is suitable. So format 1, it is of 1 byte length. So as we know that for representing for any kind of instructions, it is having 2 main factors. One is the mnemonic value and another one is symbolic value. For representing the mnemonic value, for every mnemonic value, it is having 2 hexadecimal, it is having its own opcode. That opcode is going to be represented by using 2 hexadecimal digits. If it is 2 hexadecimal digits means 1 bytes of length. Yes, of course. So for what kind of instructions the format 1 is suitable? Here. So as of course, that instruction, it should not have the instructions which should not have any kinds of operands. It should have only that opcode or the mnemonic value. Only such kind of instructions we are using format 1. So the format 1, it is of the length 8 bits. That complete 8 bits are going to be used to represent the opcode of that instruction. That opcode of that particular statement or instruction. For example, the instruction which we are using, return subroutine. What is that return subroutine? As we know that a program, it might be having one main routine and it might be having n number of subroutines. So the subroutine, it might be called anywhere in that main program. So when the subroutine is called, the control must be jumped to the subroutine. So once the subroutine is being executed, again the control must be transferred or returned back to the main routine itself. So for that, to return that control to the main routine after executing the subroutine, so we are using the instruction return sub. So for that return sub, that is the OR sub instructions, we are not using any kind of operands here, because the return address, whatever the return address where actually the control has to be transferred, that return address, it is present in that linkage register. By default, whenever we are using the OR sub instruction, when we are using that OR sub instruction, by default it is going to refer that linkage register to get the address where actually it has to be transferred, where actually that control has to be transferred. So the return subroutine instruction, it doesn't require any kind of operand field, because by default it is going to refer that linkage register value for such kind of things. So means the OR sub, it is more than enough to represent the value. So means OR sub, which is used to which is used to transfer the control to the main routine. So means it requires only that thing. So for representing, yes, of course, this OR sub is an instruction. So the opcode for that instructions, opcode for that instruction, it is 4C. The opcode for OR sub instruction is 4C. To get the object code for this instruction means it is only that 4C. That is 4 is nothing but 0, 1, 0, 0, 12, it is C. So means 4C. So this is the example for the what format 1 instruction set in SIC machine architecture. So means the instruction or the statement which is having only that operand field, operator field, not any kind of operand field. For such kind of things, we are using the format 1. So means because the length, it is only 1 byte, to represent the opcode of that any kind of operators, so only 1 byte is enough. So for this, just we are using what instruction, it is OR sub. Next I will move to format 2. For what kind of instructions the format 2 we are using? So the format 2, it is of 2 bytes length. It is of 2 bytes length. Among those 2 bytes, the first 8 bits, which is used to represent the opcode of that instruction, whatever the instruction it might be, the opcode of that instruction, and the next 8 bits, which is used to represent the register 1 value and 4 bits to represent the register's number R1 and R2. So for this kind of instructions, just we are using what? The format 2 instruction. So for example, so when we want to compare the values between the 2 registers, when we want to compare the values between 2 registers, we are using the instruction name, it is comparison. So here, as we know that every register, it is having its own number for representing single digit number. Accumulator, it is 0, base register, it is 3, special purpose registers, that is the F, it is 6, SNT, it is 4 and 5, linkage registers, it is 1, like that. So it is having its own numbers. To in that object code, instead of using that register name, just we are using its number there. So means for that, when we want to compare the values, S of course the register length, it is of 24 bits. For representing that register number, only 4 bits is enough. To represent 0, S of course 0, 0, 0 is enough. For representing 4, 0, 1, 0, 0, 0, it's enough. So in this case, when we want to compare the values which are there between the registers, we are using format 2. So means the opcode length, object code length for that particular instruction, 2 bytes is enough. So in this case, comparison between accumulator and the register S. So what this instruction says means, it is going to comparing the value which is present in an accumulator and the register S. S is a A is the accumulator is the special purpose register, S is the general purpose register. So in this case, for example, accumulator if it is having the value 10, the register which is having the value 5, it is going to comparing these two values 10 and 5. Accumulator value is greater than S, so then it is going to set the conditional code flag bit as greater than. Conditional code flag bit as greater than. After that only some kind of jump instructions will be executed. So right, so to represent these values, so here to represent these values, as we know that the number for accumulator it is 0, the number for S it is 4. The number of that register it is accumulator it is 0, the number it is for 4. So what is the opcode for? What is the opcode for comparison? Comparison, the opcode it is A0. The comparison, the opcode it is A0. So means for opcode for every instruction we are using, to represent the opcode for every instruction we are using 2 hexadecimal digits. 2 hexadecimal digits from 0 to 9 hexadecimal digits is same as the decimal value, and from 10 to 15 we are using an alphabet that is A to F. A is nothing but 10, B is nothing but is 11, C is 12, like that. So in this case, the opcode for comparison it is A0, the number of the register A it is 0, the number of register S it is 4, right. So means to get the object code for this instruction, as of course the instruction format should be like this. So means the first 8 bits, what the opcode of that instruction, that is 10, 0, 1, 0, 0, 1, 0, 1, 0 and 0, 0, 0, and the number of an accumulator it is 0, and the number of the general purpose register S it is 0, 1, 0, 0. So this is how actually we are going to represent the same instruction by using the instruction format. After that grouping of 4 digits, so then we will get an object code for that one. So what is that? A004. It is an object code for this instruction which is being done by an assembler. Object code for that particular instruction. So this is how actually we can use the format 2. Format 2 for the instruction which is required only 2 bytes. So means for that, when we want to compare the values between 2 registers, when we want to perform some kind of arithmetic operations between 2 registers, for such kind of instructions we can use the format 2 instructions. For example, additional between 2 registers, that is A comma S. For that also we can use format 2. So for such kind of instructions only 2 bytes are enough. So hence we will go with format 2 here. So next one is format 3. So this is very important here. Format 3. So format 3 it is of 3 bytes length. So among those 3 bytes, so here since the SIC-XC it is supporting different kinds of addressing modes. In SIC it was supporting only 2 addressing mode, either direct addressing mode or index addressing mode. But in a SIC-XC it is supporting different kinds of addressing mode, that is immediate addressing mode, indirect addressing mode, direct addressing mode, some kind of relative addressing mode, that is base relative and program counter relative addressing mode. Such kind of addressing modes which are available in the SIC-XC machine architecture. So for such kind of things, that is it is providing different kinds of instruction formats to fetch the values from the memory. So in this case, that is the format 3. Format 3, most of the instructions will be there on the format 3 only. So because of it is of 3 bytes, but when we can't fit the value in 3 bytes, so then we will go with format 4. So just I will give some example for such kind of things. So here the format 3, here we are going to dividing that format 3 instruction format in different parts. So the first 6 bits which is used to represent the opcode. Opcode length it is of 1 byte, 2 hexadecimal digits, but here we are using 6 bits. But when we are writing that opcode for that instructions, we are going to completely write that 8 bits in 8 different fields till now. So after that we are going to changing the addressing mode bits here. So but the opcode, for representing the opcode here, 6 bits we are using. So there are different kinds of flag bits just we are using to represent different kinds of addressing modes here. So each flag bit, it is of length, it is of 1 byte each. N, I, X, B, P, E. So these are all the different kinds of flag bits which are available, which is what supporting in that format 3. So 6 plus 6 is 12. Next 12 bits among 24 bits, whatever the next 12 bits which is used to represent the displacement value. So there is a difference between an address and the displacement. There is a difference between an address and the displacement value. In format 3, the first 6 bits which is used to represent the opcode, the next 6 bits which is going to represent what kind of addressing mode, in which addressing mode the instruction it is. So it is going to telling that information, and the next 12 bits is the displacement. It is the displacement value. So here N stands for we are using indirect addressing mode, indirect addressing. I for immediate addressing mode, and X for it is for indexed addressing mode. Indexed addressing mode, and B is for base relative addressing mode. P is for program counter relative addressing mode, base relative and the program counter relative addressing mode, and E is for identifying whether that instruction is in format 2 or format 3, which is used to represent either format 3 or format 4. For that we are using the flag bit, it is E. So if it is 0, it is in format 3. If it is 1, it is there in format 4. So but combination of these register values, these bits which are going to represent different kinds of addressing modes here, right? So N bit which is used to represent the indirect addressing mode, I for immediate addressing mode, X for index addressing mode, B for base relative, and E it is for bifurcating that on which format the instruction it is, whether it is format 3 or format 4, right? So in this case, first let's see how actually we are going to represent that NIXBP bits here. For direct addressing mode, immediate addressing mode, there are different kinds of addressing modes are there. So here just I'll brief about the representation of those bits whenever when it is 1, when it is 0, like that. So in this case, if N bit it is 1, I bit it is 0, so then it is indirect addressing mode. Indirect addressing mode, it might be with base relative or program counter relative. Base relative or program counter relative. So if the index register bit is 0, if it is 1, then it is immediate addressing mode. It is in immediate addressing mode. So let's take some example here. If both the bits N bit and I bits are 1, N bit and I bit are 1, so means the remaining bits are 0 here. the remaining bits are 0. So means is nothing but it is direct addressing mode. It is direct addressing mode in SIC XC mode. In SIC XC mode. So here 1 and 1, either it is also called as simple addressing mode or direct addressing mode. So in the direct addressing mode, both N and I bits are 0, the remaining bits are 0. So for calculating the target address, we are going to considering that displacement value. What are the bits which are present in this displacement field? So that will be considered as the target address. So means that will be the actual physical address to get the value. That is the actual physical value address to get the value. So this is called as direct addressing mode or simple addressing mode for SIC XC. Suppose if N bit it is 0, I bit is also 0, the remaining bits also 0 here. The remaining bits is also 0. It is also called as direct addressing mode or simple addressing mode, which is at SIC what architecture or SIC mode. So in here also the target address. So just we are taking that displacement value itself. The displacement value itself. So next, if the N bit it is 1, if the N bit it is 1, I bit it is 0, if X bit it is 0, B bit is 0, if the program counter relative bit it is 1, if E bit it is 0. So means is nothing but this instruction is what? Indirect addressing mode along with the program counter relative. So means indirect with program counter relative addressing mode. So to get the target address for this, we are using by adding the displacement value plus the current program counter value. At that time, what is the program counter value? Just we need to consider. So if the N bit it is 1, if the N bit it is 1, if the N bit it is 0, if the I bit it is 1, X bit it is 0, this is 0, this is 0 and this is also 0. So then it is purely immediate addressing mode. So for that we are using the target address. So immediate addressing mode means the value which is required for that instruction or for that statement immediately available in that particular instruction only. That is called as immediate addressing mode. So the target address is of course the displacement value only. So here if both the bits are 1, if index register it is 1, base register it is 0, program counter is 1 and the E bit it is 0 means this is direct addressing mode while calculating the target address we also consider the index register value as well as the program counter register value. So means direct addressing mode with index and the program counter relative. So for that we are going to calculating the target address. We are using displacement plus the content of the program counter plus the content of the index register. So here like this we are going to identifying what kind of addressing mode is for that particular instruction. So this is the simple way to get the address for different kinds of instructions. I will take some examples for these kind of things along with that program. So then I will explain how actually these instructions are going to be worked. What is displacement, how actually we can calculate the displacement and all. So here this is how actually we are going to identifying different kinds of things, different what addressing modes which are available, which is available at the page number 473 for SIC XC machine architecture. For simple addressing mode, immediate addressing mode, indirect addressing mode, for everything there are different kinds of patterns which are available. So just you can refer that also. So next I will take a simple example for this. For that instruction, the format 3. For that, just I want to take a simple example here. What? Load accumulator with an immediate value 3. So this instruction is saying that load accumulator, let us assume this program, this statement is in SIC machine architecture. So means load accumulator with an immediate value 3 here, with an immediate value 3. So means when we are using to represent an instructions in SIC, in SIC it is having only two types of instruction, direct addressing mode and the index addressing mode, but in SIC it is supporting different kinds of addressing modes only. So here for immediate addressing mode we are using this symbol. If it is indirect addressing mode, we are using @ symbol in the operand field. So if it is what format 4 instructions, just we are using plus symbol. So just we will show all the examples in later session, right? So here this is simple example just I have taken. It is in the format 3. So means what this instruction is saying is, so here immediate load accumulator should be loaded with an immediate value 3. So means accumulator should be loaded with the immediate value 3. This instruction is saying like this. So for representing this in format 3, this format 3, right? So in the format 3, as we know that the first 6 bits which is used to represent an opcode. So the next 6 bits which is used to represent what? The different kinds of flag bits, NIX, BPE, to represent the different kinds of addressing modes, and the next field which is used to, how many bits? That is a 12 bits. 12 bits which is used to represent the displacement value. That displacement value. Since this instruction is immediate addressing mode, first we should know what is an what is an opcode for LDA. The opcode for LDA, it is 0, 0. An opcode for LDA, it is 0, 0. It is at the page number 470. You can see an opcode for each and every instructions of SIC and SIC machine architecture along with the memory calculation. So the first 6 bits. So first what we need to do is, so first we have to write the complete 8 bits here. For each hexadecimal digits, we are going to representing by using 4 binary bits. So means 0, 0. First write the complete opcode in that format. The complete opcode in that format. After that, we can change it. So what is the displacement value in the immediate addressing mode? Immediate addressing mode, what actually it is saying is, in the displacement field, it is having the value which is present in that instruction. What is the value which is present in that instruction? That immediate value, it is 3. So means it is of 12 bits length. So hence we are going to representing 3 in the form of 0, 0, 3 like this. So means write like this, 0, 0, 0, 0, 0, 1, 1. 0, 0, 1, 1. So after that, we have to change, we have to write the corresponding bits. So it is in format 4? No, it is in format 3. So hence the A bit should be 0. So this instruction, it is clearly saying it is purely what? Immediate addressing mode. So hence it is not related to any kind of program counter or base relative. So hence the P bit and the B bit should be 0 here. So the next, it is not related to any index registers are there in this operand field? No. So now the index register value is also 0. So now we need to change the bit. Yes, of course, it is purely immediate addressing mode. Hence we need to set the immediate bit as 1, n bit as 0. N bit as 0. In this way, just we are going to calculating what that object code for this instruction. For that instruction. So means after writing this, so what we have to do is we have to group the 4 bits each of this instruction format. So then we have to write the equivalent hexadecimal digit for each group 0, 1, 0, 0, 0, 3. So this is an object code which is being created by an assembler while assembling that program 003. So what is the length? What is the length? How many hexadecimal digits are there? 6 hexadecimal digits. So means the length of that instruction, it is of 3 bytes. So we will take some more example for the same in the later session. So this is how actually we are going to represent what the bits, the addressing modes in the instruction format. So just have taken a simple example here. So we will take some other examples also. So next thing, it is format 4. Next one, it is format 4. So the format 4, when we are going to, almost all instructions are based on format 3 only. Some of the, when those instructions cannot be fit in format 3, so then we will go with format 4. So for what kind of instructions we will go with that format 4? Just let's have a look on this. So in this case, format 4 is of course the instruction format or instruction length, it is 4 bytes, not 3 bytes, it is 4 bytes. Among 4 bytes, the first 6 bits which is used to represent what opcode, like format 3 only. So the next 6 bits which is used to represent the addressing mode bits NI, X, BPE, each which is going to be represented by 1 bit. So the next it is, each flag bit which requires 1 bits each. The next which is used to what? An address. What are the remaining bits? Or 20 bits. 20 bits are used to represent address, but in the format 3 we were using 12 bits of displacement field. There is a difference between the displacement field and the address field. Displacement field and address field, there is a difference, but in the format 4, instead of displacement, directly we are using its address. For what kind of instructions it is required an address? So when we cannot fit that value in 12 bit of field, the displacement field in the 12 bit of field, so then we will go with the format 4 by using its address. For example, so here, just I'll take some example here. One instruction is there, that is the J sub instruction, jump subroutine. The subroutine name is redirect. Jump subroutine. So means jump subroutine means it is so when we want to call a function, so to jump to a particular subroutine which is present in the same program. So for that just we are using jump subroutine. So let us assume this instruction is at the memory location 0003. Is at the memory location 0003. This is the logical address. That is the user, means just it is going to be created along according to that what the user has given. That is called as logical address. So while loading into that primary memory, that physical address will be changed. There is a difference between logical address and physical address here, right? So let us assume what that instruction is saying is jump subroutine redirect. After this J sub, so it is having lot of instructions here. The redirect is at the memory location 1036. The redirect, suppose it is having some value, load accumulator with 0. So it is having some instructions. So means whatever the subroutine, whatever the operand fields which we are using in that program, that operands must be there in label field to refer. So in the label field, it should appear only once in that program. So means the J sub instruction is at the memory location 0003, where actually the redirect which is there at the memory location 1036. So whatever the instruction it might be, the assembler is going to try with format 3 only. So to find out the displacement, value for that instruction. If it is fit into that format 3, so then it will not go with format 4. If it is not able to fit in format 3, so then it will go with format 4. So for example, in this case, first it is going to trying with format 3 only. So in the format 3, what actually it is? So in the format 3, the first instruction, the first 4 instructions, sorry, first 6 bits which is used to represent what? That opcode, right? So here just we have to find out the displacement. So in this case, the assembler is going to trying to find out the address for each and every instruction. First it is going to try with program counter relative addressing mode with direct addressing mode with program counter relative addressing mode. So means in this case, so if it is direct addressing mode with program counter relative addressing mode, as we know that the program counter is pointing to this instruction, it is fetching this instruction to be executed. So once that instruction is fetched out, immediately the program counter value is going to be incremented for the next instruction. Now the program counter value, it is 0006. So in this case, yes, of course, to get the target address we are using. So if that instruction direct addressing mode with program counter relative addressing mode. So assembler is trying for all the instruction, that is only. If it is not possible, so then it will go with base relative addressing mode. So to find out the target address, it is having the formula content of the program counter plus displacement value. Content of the program counter plus displacement value. So means here we don't know the displacement value, we know the target address. So what is the target address? JSUB, it has to jump to the subroutine redirect. We know that where actually the redirect is there, at the memory location 1036. That is the target address. So we know the target address, we know that program counter value, we don't know the value of displacement. To find out the displacement value, so what is the formula then? Displacement is equal to target address minus program counter. So what is the target address? 1036, that is the redirect value, minus what is the program counter? 0006. So then what is the displacement value? It is 1000. So this is the displacement value here. Can we fit these 4 digits in that 12 bits of field in format 3? So because we can fit only 3 hexadecimal digits in displacement field. So but what is the displacement we got here? For this instruction, it is 1000. It is 4 hexadecimal digits. That 4 hexadecimal digits we cannot fit in this displacement field in format 3. So for such kind of instruction, instead of format 3, we are going with format 4. We are going with the format 4 instructions. So in this case, yes, of course 1000, it is of 4 hexadecimal digits. We cannot fit this 4 hexadecimal digits in 3 bits of hexadecimal field in that format 3. So hence, for such kind of instructions, we are using format 3 instead of, format 4 instead of format 4. We are using format 4 instead of format 3. So in this case, instead of using the displacement value, directly we are using its address. So for this, the target address that is address only. That is the address only. So what is the opcode? What is that instruction? JSUB. What is the JSUB? What is the opcode for the JSUB? It is 48. So here the opcode for JSUB, it is 48. What is the address of redirect? It is 1036. The redirect, it is at the memory location 1036. So when we want to write the instruction format for that, it is the opcode right. So what is the opcode for the JSUB? 48. First write it down, 0100, again 1000. So I don't know the remaining bits now. So now we are going with the format 4. So whatever the address, the direct address, just we have to write in that what field, that is 1 0 3 6 0 1 1 0. So the next thing is it is direct addressing mode. Both n bit and I bit should be 1, and E bit, because it is format 4, E bit should be 1. We are not using any kind of program counter relative, any kind of base relative, any kind of what index base register, sorry, index registers. So hence the remaining bits should be 0. So now we have to get an object code for this instruction. So what is that instruction? What is the object code? It is 4. 8 plus 2 10, 10 plus 1 it is 11, 11 means it is B, 4B, it is 1, 4B, it is 1, 1, 0, 3, 6. So means for this instruction, what is that instruction? For this instruction, the object code it is 4B, 1, 1, 0, 3, 6. 4B, 1 1 1 0 sorry 1 0 3 6. 4B 1 4B 1 next BP, sorry, 20 bits, right? So means just we have to set the preceded 0 here. So instead of 0, just we have to get 0 1 0 3 6. So means instead of that one, so just we have to put here 4B 1 0 4B 1 0 1 0 3 6. So this is an object code for that instruction. So means the object code length it is 4 bytes. So these are the 4 different kinds of instruction formats in what SIC XC programming. So in this case, please do remember the assembler is going to identify or find out the object code for each and every instructions. So for such kind of things, it is going to following this rule. So whatever the instruction it might be, the assembler is trying with to get an object code. First it is going to trying with what direct addressing mode along with the program counter relative addressing mode format 3. If it is not possible, so then it will go with base relative. So then it will go with indirect addressing mode or some kind of relative addressing mode. If it is not possible with format 3, so then it will go with format 4. So now I am ending up this session today's session. So we will continue the same in the upcoming session. Thank you.